The next theorem is, if sequence Sn and sequence Tn are bounded sequences of real numbers, bounded sequences of real numbers, and if every term of sequence Sn is less equal every term of sequence Tn for any positive integer n, then the limit supremum of sequence Sn is always less equal limit supremum of sequence Tn, and similarly limit inferior of sequence Sn is less equal limit inferior of sequence Tn. If for every nth term of sequence Sn and Tn it should satisfy Sn is less equal Tn. So the proof is, so let sequence Sn is less equal TL for each positive integer n, and Sn Tn are sequences of real numbers. So if we consider the two sets, least upper bound of Sn, Sn plus 1, Sn plus 2, and the other set is least upper bound of Tn, Tn plus 1, Tn plus 2, and so on. So what the comparison would be? So definitely if each Sn is less equal each Tn, right, for each positive integer n, so then least upper bound of this set will be definitely less equal least upper bound of this set, right? And similarly, what you can say about the greatest lower bound of same set? Greatest lower bound of the same sets. So definitely if Sn is less equal Tn, so the same relation would be there, right? So letting as n tends to infinity, so what we get, taking limit on both the sides for both these expressions or both these inequalities, so it means that limit of least upper bound and limit of greatest lower bound, so it is supremum and it is also supremum. So what we get, limit supremum superior of sequence Sn is less equal limit inferior of sequence Tn, and similarly limit inferior of sequence Sn will be less equal limit inferior of sequence Tn. Now see example. Is that if sequence Sn is greater than Tn, or finite n, finite positive integer n, it is not always true that limit superior of Sn plus Tn is equal to limit superior of Sn plus limit superior of Tn. So for example, if we consider Sn to be minus 1 raised to n for positive integer n and Tn to be minus 1 raised to n plus 1, so then definitely sequence Sn plus Tn will be 0, right? This is minus 1 raised to n, this is minus 1 raised to n plus 1. So if the nth term here is minus 1, then the nth term here would be plus 1. So the definitely it will be a constant sequence of 0 for all positive integers n. But so implies limit superior of Sn plus Tn would be 0, but limit superior of Sn would be 1, limit superior of Tn would be 1, and it is not satisfied, right? So and note that Sn Tn are bounded sequences in this case. Right. So in case of limit superior, the equality will definitely does not hold always. So the theorem related to that is, if sequence Sn and sequence Tn are bounded sequences, of real numbers, then the limit superior of Sn plus Tn would be definitely less than or equal to limit superior of Sn plus limit superior of Tn, right? It is a statement A, and other thing is limit inferior of Sn plus Tn would be greater equal limit inferior of Sn plus limit inferior of Tn. So just prove the statement of the theorem. So let me consider this Mn to be a least upper bound of Sn, Sn plus 1, Sn plus 2, and so on. Similarly, let me choose Pn to be least upper bound of Tn, Tn plus 1, Tn plus 2, and so on. As it is least upper bound, so then for some k greater equal n, the kth term of the sequence would be definitely less than or equal to Mn, because it is a least upper bound, right? And the kth term of the sequence Tn would be less equal Pn, as it is also a least upper bound for nth and latter terms, right? And so therefore their addition sk plus tk would have been less equal the sum of the least upper bounds of the nth and latter terms. So it implies that for k greater equal n, mn plus pn, mn plus pn is an upper bound for the set Sn plus Tn, Sn plus 1 plus Tn plus 1, Sn plus 2 plus Tn plus 2, and so on. So therefore, least upper bound of this set Sn plus Tn, Sn plus 1 plus Tn plus 1, Sn plus 2 plus Tn plus 2, and so on. So least upper bound of this set would be what? As it is every term for k greater equal n, every term sk plus tk is less equal mn plus pn. So least upper bound of this set would have been less than or equal to mn plus pn, definitely. So now we let as n tends to infinity in this case. So let us see what happens. So letting n tends to infinity. So what we get? Limit n tends to infinity, least upper bound of Sn plus Tn, Sn plus 1 plus Tn plus 1, Sn plus 2 plus Tn plus 2, and so on. And it is less equal limit of mn plus pn. And by the definition of limit of the sequence, we can write it as limit of mn and limit of pn, and it is nothing but limit superior and limit inferior, and it is also nothing but, it means least upper bound. It means least upper bound of sequence Sn, Sn plus 1, Sn plus 2. This is least upper bound of sequence Tn, Tn plus 1, Tn plus 2, and so on. And definitely it is a least upper bound and its limit. So it is nothing but limit superior of the sequence Sn plus Tn and is less equal. This thing is limit superior of sequence Sn, and this thing is nothing but limit superior of sequence Tn. So it is a part A. Now part B. Let me consider Mn to be a greatest lower bound of sequence Sn, Sn plus 1, Sn plus 2, and so on. Similarly, Pn I choose to be, it is small p, greatest lower bound of Tn, Tn plus 1, Tn plus 2, and follow the procedure we have done. As it is a greatest lower bound, so for, let me choose k instead of k, let me choose r. For r greater equal n, the kth term of the sequence Sn would be greater equal this small mn, and kth term of the sequence Tn would have been greater equal the greatest lower bound Pn. It is true for we have choose it to be r, Sr and Tr. So SR plus TR would have been greater equal MN plus PN for all R greater equal N. And as we have seen, therefore this Mn plus Pn is a lower bound for the set Sn plus Tn, Sn plus 1 plus Tn plus 1 and so on. So greatest lower bound of this set Sn plus Tn, Sn plus 1 plus Tn plus 1 and so on would have been greater equal this Mn plus Pn. So now letting as n tends to infinity, so we get limit of greatest lower bound of Sn plus Tn, Sn plus 1 plus Tn plus 1 and so on would have been greater equal limit of Mn plus Pn, it is small p, but then it would be limit of Mn plus limit of Pn, and it is nothing but limit inferior. It is limit inferior for the sequence Tn, it is limit inferior for the sequence Sn, and definitely it is a limit of greatest lower bound, so it is limit inferior of sequence Sn plus Tn and is greater equal limit inferior of sequence Sn plus limit inferior of sequence Tn n approaches to infinity. So we have proved this theorem, right? So now let us move to the last theorem, and it is the statement is that any bounded sequence of real numbers, any bounded sequence of real numbers has a convergent subsequence. So if we consider any bounded sequence of real numbers, so we have to show that it has a convergent subsequence. So let Sn be a bounded sequence of real numbers. So what we wish to show, it has a convergent subsequence. So as it is a bounded sequence, so let me suppose limit superior of sequence Sn is m, as it is bounded, so limit superior is m. Now we construct a subsequence Snk which converges to this limit superior of the sequence Sn. So as it is a bounded sequence, Sn is bounded sequence, so as Sn is Sn is bounded. So it implies that there are infinitely many n such that the nth term Sn is greater than m minus 1. The nth term Sn is greater than m minus 1. And so let me choose. Let n1 be one such value. It means that is n1 is positive integer and Sn1 is greater than m minus 1. So similarly, as there are infinitely many n such that Sn is greater than m minus half. Sn is greater than m minus half. So let me choose n2 be one such value. That means that is n2 is positive integer and Sn2 is greater than m minus half. So continuing by this way, for each integer k, we can have a positive integer nk such that nk is strictly greater than nk minus 1 and the nkth term of the sequence is strictly greater than m minus 1 by k. Therefore, for given any epsilon greater than 0, we find a positive integer n such that the nth term of the sequence is less than m plus epsilon. M plus epsilon for all n greater equal n. And now we choose the positive integer k. So such that 1 upon k is strictly less than epsilon and nk is greater than the positive integer n, then for k greater equal k, it implies 1 upon k is less than epsilon and nk is greater than n. Therefore, from this equation and from this equation, what we get? Nk is strictly less than m plus epsilon. Snk is less than m minus 1 by k from this, and m minus 1 by k is definitely less than m minus epsilon. And it implies what it implies. Minus epsilon less than snk minus m is less than epsilon, and it means modulus of snk minus m is less than epsilon. So it implies that the subsequence snk is converges to m, right? So we have shown that if sequence Sn is a bounded sequence, then it converges to, it has a convergent subsequence, right?